Now we will take a look at the graphs of the trigonometric functions. We'll begin with the sine and cosine graphs. So here we have the graph of the sine function. Here we have the graph of the cosine function. Right? So notice the shapes. Right? The shapes are practically identical. In fact, the shapes are identical. The only difference is where these humps appear in sine and cosine. Now, one full rotation is considered to be one period. So remember, the period of both sine and cosine is 2 pi. So from one peak to the next peak would be one full period, one full rotation. Or you could look at one valley to the next valley, right? Or, as in the case in the figure, halfway point to the halfway point. And then cosine, of course, is the same. Now, the sine and cosine have several distinct characteristics. We've already studied them. I will relist them now. First, they are both periodic functions with a period of 2 pi. Second, the domain of each is the all real numbers, and the range is -1 to 1 inclusive. Third, the graph of y equals sine of x is symmetric about the origin. Fourth, the graph of y equals cosine of x is symmetric about the y-axis. Any function that has the same general shape as either the sine or cosine function is known as a sinusoidal function. And the graph of such a function is known as a sinusoidal wave. Examples of sinusoidal waves are the ocean waves, ripples when a pebble is tossed into a pond, and heart rhythm. The general forms of sinusoidal functions could be one of these two, either y equals a times the sine of bx minus c plus d, or y equals a times the cosine of bx minus c plus d. So we're going to go ahead and examine both of these functions a little bit more in depth, and we start with a sine of x and a cosine of x. Now, since the range of both sine and cosine is -1 to 1, we can write the absolute value of sine of x is less than or equal to 1, and the absolute value of cosine of x is less than or equal to 1. The maximum value of the absolute value of sine of x and the absolute value of cosine of x is called the amplitude of the function. So if we're just looking at sine of x and cosine of x, they each have amplitude of 1. But we're looking at the absolute value of a sine of x. Using properties of absolute values, we can write this as the absolute value of a times the absolute value of sine of x, and this is less than or equal to the absolute value of a. Similarly, the absolute value of a cosine of x is less than or equal to the absolute value of a. And so absolute value of a is the amplitude of both of these functions up here. If a is less than 0, then we happen to have a reflection across the x-axis, but the amplitude is still the same. Now let's examine the functions y equals sine b of x, or sine of bx, and y equals cosine of bx. Now the period of both sine and cosine is 2 pi. So one full period of these functions can be represented 0 less than or equal to x less than 2 pi. Right, so for these two functions up here, we'd have 0 is less than or equal to the absolute value of b times x, which is less than 2 pi. If we divide by the absolute value of b, we'll get 0 is less than or equal to x, which is less than 2 pi over the absolute value of b. And so the period is given as p equals 2 pi over the absolute value of b. Again, if b is less than 0, we have a reflection across the y-axis, but the period is still the same. So to see this, let's go ahead and determine the period sine of pi over 6x. So what we have to have is we have to have 0 less than or equal to pi over 6 times x, which is less than 2 pi. So we can divide by pi over 6 or multiply by 6 over pi, and we get 0 is less than or equal to x, which is less than 2 pi, I don't know why I wrote that up there, 2 pi times 6 over pi, which is just simply 12. So the period is 12. Now we'll go ahead and examine the general forms of the sinusoidal functions. We do so by rewriting them in this form, and I'm only going to go over one. The other one is identical, right? So a sine of b times x minus c over b plus d. So all we did is we factored out the b, right? Remember, the original form was a sine of bx minus c plus d. So all we did was factor the b out from in here. Now, if you factor out a b from c, you have to be left with c over b, right? Because remember, if you distribute in, so if we were to distribute this b back in, we have to get bx minus c, which we do. This value, the c over b, represents a horizontal translation. For sinusoidal functions, we call this a phase shift. D simply represents a vertical translation. We now summarize this entire discussion on the next slide. And I'll let you read through that. We will now go ahead and sketch the graph of a sine function. So the first thing we want to do is rewrite 3 times the sine of pi over 4x minus pi over 4 by factoring out that pi over 4. We're left with x minus 1. So the amplitude here is 3. The period would be 2 pi times 4 over pi, which is 8. We have a phase shift of 1. And we have no horizontal translation. Okay, so let's go ahead, draw our coordinate axes. Okay, here's our x, here's our y up here. So our amplitude is going to be 3, so let's go ahead and draw 3 tick marks on the y-axis. We have a phase shift of 1. Now remember, sine normally starts at the origin. Here we're going to have it right here. It has a period of 8. So after 8, it has one full rotation. Well, if that's 1, 2, 3, there's 4, minus 1, minus 2, minus 3, minus 4. So we'll draw it out there. Now it's just a matter of it's going to go up to 3. We'll then drop back down to 0. Right, this here comes down to minus 3. Could be somewhere there, I don't know. It has to cross I'm sorry, that should not, I really messed up. It goes out, not to 4, I'm sorry, it goes out to 5. So I'm going to need another tick here. So it's going to hit 0 here, 0 here, 0 here, and then somewhere out there. Let's try this again. So it still goes up to 3. I want to draw better. Drops back down to 0. So right there. This comes down this way to -3. It'll cross at 0. And eventually come back up to 3. And so we'll say that is not one full period. It'll be out to here. Something like that. It doesn't have to be perfect, it's just a sketch. We will now go ahead and examine the remaining 4 trig functions, starting with tangent. So this is the graph of the tangent function. Notice that the tangent function has vertical asymptotes. The general form of a tangent function is y equals a tangent of bx minus c plus d. We will start by analyzing a times tangent of x, just like we did with sine and cosine. However, unlike the sine and cosine, the tangent function has no maximum nor minimum, right? You can see that here. At the asymptotes, it goes up to minus infinity and down to minus infinity. So it has no amplitude. So in this case, a is only going to behave as a stretching factor, a vertical stretch or compress factor. If we look at the tangent of bx, recall that the tangent is pi periodic, so one full cycle of tangent is represented by 0 less than equal to x less than pi. So one full cycle of this function up here, this tangent of bx, would be 0 less than equal to the absolute value of b times x less than pi, or, oh dear, let me rewrite this, 0 less than equal to x less than pi over the absolute value of b. So the period is p equals pi over the absolute value of b. Again, as we did with sine and cosine, we'll rewrite the general form as this. So the term c over b refers to the phase shift. However, unlike sine and cosine, the tangent also has vertical asymptotes. Now recall that tangent is sine over cosine, so tangent has a vertical asymptote whenever cosine of x is equal to 0. Since cosine of x is equal to 0 at pi over 2, 3 pi over 2 from 0 to 2 pi, and since cosine is 2 pi periodic, we conclude that tangent has a vertical asymptote at every odd multiple of pi over 2. That is, tangent has an infinite number of vertical asymptotes, and the set of all of them is the set of x equals 2n plus 1 pi all over 2, such that n is an integer. Also recall that the phase shift represents a horizontal translation. So the phase shift affects the vertical asymptotes of tangent. Specifically, if we're only considering the phase shift, the vertical asymptotes becomes x equals c over b plus 2n plus 1 pi all over 2, where n is an integer. However, we also have a period of pi over absolute value of b. This also affects the vertical asymptote. If we now account for both phase shift and period, then the vertical asymptotes become x equals c over b plus 2n plus 1 pi all over 2 times the absolute value of b, where n is an integer. And that is summarized on this slide. We wish to sketch one full cycle of this tangent function. So the stretching factor is 2. We have a period of 1, right? B is pi. We have a phase shift of -1. Right, again, if we factor out a pi from here, this becomes +1. And we have a vertical translation of negative 1. So the asymptotes we will have x is equal to negative 1 plus 1/2. So we get negative 1/2. And then we also have x is equal to negative 1 minus 1/2, which is negative 3/2. Now we only need the two asymptotes because we're only looking at one full rotation. Both of the asymptotes are negative, so we only need the left side of the graph. Let's say this is negative 1/2 here. This would be 1. This will be negative 3/2. So we have those two. And the graph is going to look something like this. So we're going to have a point down here. And it'll do something like that. For the next three functions, the secant, the cosine, the cotangent, we will not dive into derivation. Those are really simple. They follow directly from cosine, sine, and tangent. So we're just going to do the summary slide. So here's the graph of secant. So green is secant, the blue is cosine. So look what happens. So secant, essentially, is parabolas where the vertex touches either the peak or the valley of cosine. So given the function a times secant of bx minus c plus d, the stretching factor is the absolute value of a. Again, there is no magnitude of secant. If a is less than 1, we will have a reflection across the x-axis. The period is 2 pi over the absolute value of b. If b is less than 0, we have a reflection across the y-axis. The phase shift is c over b, which represents a horizontal translation. D represents a vertical translation, and the vertical asymptotes occur at x equals c over b plus 2n plus 1 pi all over 2 times the absolute value of b, where n is an integer. Here is a graph of the cosecant function. It is similar to the secant in that the vertex of the parabola is the peak or valley of the sine function. Now, given the function a times cosecant of bx minus c plus d, stretching factor is absolute value of a. Again, there is no amplitude. If a is less than 0, we have a reflection across the x-axis. The period is 2 pi over absolute value of b. If b is less than 0, we have a reflection across the y-axis. The phase shift is c over b, which represents a horizontal translation. D represents a vertical translation, and the vertical asymptotes occur at x equals c over b plus n pi over absolute value of b, where n is an integer. And finally, here we have the graph of the cotangent function. Given the function a times the cotangent of bx minus c plus d, the stretching factor is absolute value of a. Again, there is no amplitude. If a is less than 0, we have a reflection across the x-axis. The period is pi over the absolute value of b. If b is less than 0, we have a reflection across the y-axis. The phase shift is c over b, which represents a horizontal translation. D represents a vertical translation. And finally, the vertical asymptotes occur at x equals c over b plus n pi over the absolute value of b, where n is an integer. So those are the graphs of the trigonometric functions. In the next video, we will look at inverse trigonometric functions.